Section 3.4, Beyond Linear Decision Boundaries. Recall figures 3.1, 3.2, and 3.7. So let's look at those figures just to recall them. Figures 3.1, 3.2, and 3.7. So in figure 3.1, we had the sigmoid curve in 1 or 2 dimensions. So that's logistic regression. And in figure 3.2, we had a linear decision boundary, which we get when we use this decision curve. In this case, that one stems from here. Okay. And in 3.7, we had the polytope, convex polytope decision boundaries, also linear, you might say, with straight lines, etc. Okay, which you get in multinomial regression. So beyond linear decision boundaries, we've just recalled these 3 figures. Great. That's the start of the section. Logistic regression naturally yields a sigmoidal relationship, so we saw that, between the input features and the response probability. In a classification setting, this translates to linear, affine decision boundaries. Similarly, multinomial regression used for classification also yields straight line boundaries via convex polytope decision boundaries. One may then ask if these shallow neural network models can create other forms of response curves or decision boundaries, so not just straight lines. We now show that this is indeed possible via feature engineering, following a similar spirit to the way feature engineering was introduced in section 2.2. So in chapter 2, we saw feature engineering that was for the Boston housing pricing dataset, where we just added a quadratic term, for example. Enhancing the sigmoidal response. Recall first the linear regression example illustrated in figure 2.3 of chapter 2. So that was the one with the Boston housing. In display B of that figure, we won't look at that figure just now, we saw how linear regression with an engineered quadratic feature yields a curve that better fits the data. A similar type of idea may also be applied in the case of logistic regression. As an example, consider a dataset D where each observation is for a different geographic location and where the feature vector has a single coordinate, which is the level of precipitation at the location in, say, millimeters by month. Okay, so you got different geographic location, you got level of precipitation. For each observation, the associated yi, which is either 0 or 1, determines the absence 0 or presence 1 of a certain species. Observations from such a dataset are presented in figure 3.8. At locations I that are not too dry or not too wet, the species tends to be present. Okay, so at the locations here, we get species, whereas when the participation is very low or the precipitation is very high, the species tend to be absent. Okay, they don't like very wet climates or very dry climates. They like middle precipitation. Such a relationship between the precipitation and the probability of presence of species cannot be captured by a sigmoidal curve, since this function is a monotonic function of x. So this is a sigmoidal curve. Notice here that we have W1 instead of W transposed. We'll see if that's why we do that. Is a monotonic function of x. So the thing is, the sigmoid either goes down or goes up, okay, depending on what we put here for the sign. Okay. In fact, when fitting a sigmoidal curve to this data, the response plotted via the red curve of figure 3.8 tends to be almost flat in the region of the observations, because in this case, W1 hat is close to 0. So this red curve, which you see here, is the sigmoidal curve featured for this data, and it seems almost flat. I mean, in fact, what it does is very far away. It does this and it does that, but extremely far, right? So outside of the dynamic range of this. Nevertheless, if we wish to use logistic regression for this problem, we may do so via feature engineering. Similarly to the housing price example of section 2.2, we introduce a new feature. And in this case, we'll do the same type of thing. We'll take x2 to be x1 squared. With the addition of this new feature, the model as a function of the single feature, x equals x1 becomes, so this is phi of x, but you have x and you have x squared, so this is a model. Following from basic properties of the parabola, b plus w1x plus w2x, if w2 is less than 0, then we have that phi of x goes to 0 as x goes to negative infinity, or x goes to infinity. So we've got this type of thing happening here. And further, phi of x is maximized at this x, which is a maximal point of the parabola. Similarly, if w2 is greater than 0, the shape of phi of x is reversed. Phi of x has a minimum point, so we could have had, if w2 was opposite, we could have had a curve like this, if this was the right thing to present, to get, okay? If this was the right thing for the data. In both cases, phi of x is symmetric about this specific x, okay? The details are not so important, but the point is that you see that with feature engineering, we took the sigmoidal curve and we actually managed to get a different type of curve. The general setup of polynomial feature engineering. As in the example above, in general, it is quite common to use powers for feature engineering. And this makes the linear combination of the engineered features a polynomial. In examples with a small number of features, such as p equals 1, where we had that above, we can tweak feature engineering visually. However, when p is large, other performance-based methods are needed. When there are initially p input features, we can automate the creation of more features by choosing each new feature as a power product or monomial form, namely this type of thing. x1 to the power k1 times x2 to the power k2 times up to xp to the power kp for some non-negative integers k1, k2, kp. Of course, they can be 0 and then that feature is not there. With such a process, it is common to limit the degree by some constant r, namely the joint degree of everything k1 up to kp is going to be less than or equal than r. Okay. For example, when r equals 2, if you have the degree at most 2, the set of engineered features is, well, first of all, you can just have the x1, x2 up to xp. And then you can have x1 times itself, x2 times itself, xp times itself. Then you can have all of the crosses, x1, x2, x1, x3, x1, x4, etc. to x1, xp. And then the last one would be xp minus 1 times xp. Okay. In this case, this new x, this x tilde, you can actually count that there are p times p plus 3 over 2 of them. And thus d is 1 plus p plus p plus 3 over 2 of them for logistic regression. Okay. And this is, as the footnote says, this holds in any case. This would be in a linear model as well when the number of parameters is 1 plus the number of features. So if, for example, there are initially p equals 1,000 features, then there are about 500,000 engineered features. We can compute that there's about 500,000 engineered features. One may, of course, cull the number of engineered features to reduce the number of learned parameters. This can sometimes be done via regularization introduced in section 2.5. So we have that in chapter 2. Let us also go beyond r equals 2 to higher degrees of monomial features. So from basic combinatorics, we have that the number of non-negative integer solutions to this equation, k1 plus theta up to kp equals L, is L plus p minus 1 factorial divided by p minus 1 factorial L factorial. Okay, so this is a combinatorial case of distributing balls into bins when the balls are indistinguishable and there's not a limit of the number of balls per bin, for example. Okay, so that's L plus, you could have written this as L plus p minus 1, choose p minus 1, this binomial coefficient. This is the number of ways of doing this. And that's when using polynomial feature scheme with the degree up to R, we have, so now let's sum this thing, this expression, this guy, from L going 0 to R, and that's the number of parameters we'll have. And for multinomial regression, D is K, or K minus 1 if you're using the statistical parameterization, times this number with the machine learning or statistical parameterization respectively, right? So for multinomial regression, you'll even have more. Using Stirling's approximation of factorials, we have that when L is significantly smaller than P, then we can actually get Stirling approximation is an approximation just for factorials, and then we can simplify this expression. And we can actually, well, we can get an approximation for it. We'll get that D is approximately P to the power R divided by R factorial for logistic regression. So, for example, if you have, again, 1,000 input features, and you say R is 4, so that means you can have up to combined derived features that take a product of up to 4 different features. We have approximately, this thing is like 40 trillion, or 42 trillion roughly. Okay, parameters, or this is the exact number. Okay. So over 40 trillion parameters to learn. Having 40 trillion parameters in a model is indeed borderline astronomical as of today, still infeasible, and you certainly won't want to have such a big model for such a big number of parameters to learn for a relatively small, well, simple model. Okay, so just for reference, today as of 2023, the biggest model has about 500 billion parameters, and that's a very complex large language model. Having 40 billion parameters in models borderline is today still infeasible. That's for non-small p, going beyond r equals 2 is rarely used in practice. In fact, in section 5.2 of chapter 5, we argue that with deeper neural networks, and this is where this book is going and where technology has gone, one may sometimes get more expressivity without creating such a large number of parameters. So feature engineering is not so common in an ad hoc way today anyway. Let's look now at versatile classification boundaries. To further explore feature engineering, let us now consider classification problems. We have seen above that both logistic regression and multinomial regression yield decision boundaries defined by hyperplanes, which may be generally denoted via h of x. Each such hyperplane has parameters b brev and w brev and rp. So brev is this funny thing above the letter, okay, which depend on the estimated model parameters in a simple manner. Decision rules for classification with given input x star and rp are then made based on if h of x star is greater than 0 or equal to it or not, where the case of multinomial regression involves multiple such hyperplane comparisons. Now, in a feature engineered scenario, the hyperplane parameters are adapted to be of larger dimension, and in place of h x star, we evaluate this h tilde x star with parameters b tilde and w tilde brev. As an example, consider a scenario with p equal 2 features where we carry out polynomial feature engineering as above with r equals 2. just taking squares and products of terms. Then the number of parameters is now d equals 6. So from 2 we got to 6, and the hyperplane becomes, we've got your intercept, the w1 x1, w2 x2, w3 x3, w4 is times x2 squared, and w5 times x1 squared and x2 squared and x1 x2. Now here, the set of input feature vectors x1, x2, and r2 that satisfies the above inequality is no longer a half space, but rather represents some curved subset of R2. We thus see that such feature engineering allows one for non-linear decision boundaries. Okay, so with such feature engineering, we get non-linear decision boundaries, right? Because this inequality, which is a decision boundary, is no longer kind of an affine inequality of a half plane because it has these quadratic terms and these product terms. Okay, that's what's going to happen. As an example, consider figure 3.9 based on synthetic data. It requires binary classification with 2 input features. Okay, so again, 2 input features, we could put things on the plane, p equals 2. In A, we see that for this type of data, logistic regression without feature engineering is not suitable. The linear decision boundary is not able to capture the pattern in the data. Okay, so let's look. So here, this is synthetic data, this figure. Okay. So, and we're just looking here at binary classification. So k equals 2, okay, and p equals 2. So you've got your 2 features, x1, x2, and you cannot do logistic regression for this because you would, well, it doesn't work well because you're just going to get this linear decision boundary, okay, and that doesn't work well. Then we continue. In B, we expand the set of features and get a decision boundary of the form 335. So exactly this thing. So let's see what this can give us. So with this hyperplanes, you already get some kind of nice way, right? So with B, you're already able to make some separation between the one class and the other class. It appears that going from d equals 3 learned parameters to d equals 6 learned parameters is worthwhile since the pattern in data is well captured in B. Tick. We may continue with the higher orders in an attempt to gain more expressivity. However, as we see in C and D, for this data, the higher order models yield obscure classification decision boundaries. In this example, these higher orders certainly appear like an overfit. Such overfitting would probably yield to high generalization error. Recall the discussion we had in section 2.5. Moreover, the new set of features become highly correlated, and that can cause difficulty in inference of parameters when taking a statistical approach. Okay, so if we went to C or for D, so with C we have quadratic, we had quartic, so R equals 4, and with D we really allowed like a whole bunch of features, right? 45 features, powers up to 8, and then the model really kind of connects to the specific data points, and it has an overfit. As another visual example, return to the synthetic multi-class classification example illustrated in figure 3.7. So in figure 3.7, we're now going to just return to this figure 3.7. You'll see it in a second. Yep. So we're going to return to this synthetic data. That's now multi-class classifications. K equals 4, P equals 2, figure 3.7. We expand the set of features for this example and plot the decision regions in figure 3.10. We'll see this figure in a second. As this is just a synthetic example, our purpose is to show that by increasing the number of engineered features, we can get more curvature in the decision boundaries. In A, we consider quadratic features, and in B, we consider an extreme case of R equals 8, which actually has 180 parameters with a machine learning parameterization. Okay. So in A, we had R equals 2. And in B, we allowed R equals 8, and there's a whole lot of features. Again, this is probably an overfit for this data. But the point is that with feature engineering, we move away from linear decision boundaries. And that is the end of this short section, 3.4. I hope you found it useful. Keep this section in mind when you go to chapter 5 and we speak about depth of neural networks. So instead of adding engineered features, we can also make the network deeper. And that actually gives networks a whole lot of expressivity. We'll speak about that in chapter 5. As always, let us know what you think in the comments below. Thank you and bye-bye.